what I'm looking at here is a hot particle of uranium, about 1 micron, that's 1/1,000,000 of a meter in diameter, which was sent in a sample from Lebanon, from the bomb site where Hassan Nasrallah was blown up by the Israelis. This is a soil sample, and we have other soil samples and also air filter samples. Why is this important? Well, if you look on the screen here, you will see that there are particles there that are clustered together. It's an image of a clustered particle, and there are a number of those particles, and we'll show you another one later where there's more clustering. There's 7 tracks in one place. And the reason that this is important is because normally the radiation from these particles, and these are alpha particles, are assessed in terms of their health effects by a risk model which is dishonest and wrong. And as a result of this, people in Iraq, where these substances have been used, these uranium weapons have been used since 1991, have an enormous increase in cancer and congenital birth defects, and the same in Gaza, and we can expect the same thing in Lebanon as well. And this has more complicated, not complicated, it has more important ramifications for the planet, for everybody living on the planet, because these particles don't stay in Iraq, they don't stay in the Lebanon, they don't stay in the places where they have been produced, because they're very, very small. They're about 1 micron in diameter. This one is 1 micron in diameter, and they float all over the place and people inhale them, but of course most of all the people living close to the bomb sites inhale them. And so what is the real problem about this? The problem about this arises from the risk model of which is currently used, and I'm going to ask Miranda here to be used as a model. This is a human being, we'll assume, although she's very nice. And what happens is that there is such a thing as natural background radiation, and the natural background radiation in the environment, which is mainly gamma radiation and radiation from space called cosmic rays and so on, they send down tracks, like the tracks that you see here. What you're seeing on the screen, what you saw on the screen here, are the ends of the tracks. So basically the track is coming towards you. And I have some tracks here to show you how this works. So Miranda can demonstrate this. What you have here is you have a uranium particle. You see, this is a particle, and each one of these is an alpha particle track. And what you're looking at the screen there, where you see these bubbles all clustered together, is you're seeing it from the point of view of the observer. The microscope is looking down at a piece of plastic in which these tracks have hit the plastic and made little bubbles at the end of it. So that's what you're looking at. And you can count the number of tracks on the piece of plastic in the field of view, because you've got a microscope, and the microscope is set up at 100 times magnification. And these tracks are approximately 30 microns long. But what you see is the end of them, and the end of them is about 20 microns or so across. So you're looking at this part. Now back to Miranda. What happens is that when the current radiation risk model, the one that underpins all of the development of nuclear energy and the understanding of the health effects of uranium weapons, all these things that currently regulate the laws relating to how much radiation you can receive, and regulating the laws that enable the military of the United States and Britain to continue to use uranium weapons. And they do so on the basis that these tracks are irrelevant. What they do is they dilute all of the energy into the whole body. So if you take natural background radiation to Miranda, she'll get a track there and a track there and a track there and a track there. And if you take a Geiger counter and you hold it, it goes click, 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 like that, okay? And each one of these is a track, and it goes zoop through Miranda, and zoop through Miranda, and zoop through Miranda, and so on. All her life. All her life. And of course then she dies at the end of it when she's an old woman. because these tracks accumulate damage into the cells of the body. And so as the cells replicate, they replicate more damage as they get older. Of course, as they get older, each cell that is the daughter cell of the cell that's damaged will copy that damage down to the daughters, and then that will copy to the granddaughter cells, and so on, all the way down. So by the time you get old, the damage will have accumulated to such an extent that the cells don't work anymore, and you start to look old, and then you die. And this is lifespan, but it's also cancer, because accumulated damage is the cause. Accumulated genetic damage is the cause of cancer. When you accumulate sufficient genetic damage, the cell can go mad and produce a tumour. Now, Professor Goodhead, who I worked with, who was the chair of the Kerry Committee examining radiation risk from internal emitters that was set up by the British government in 2001, he made a famous calculation about the number of tracks that each cell got in a year. And on the basis of a simple calculation, back of the envelope calculation, you can figure out that each cell in the body, and there's 10 to the power 13 cells in the body, and we know that because we measured them, or scientists have measured them, I haven't measured them. And each of the 10 to the 13 cells in the body receives one track in a year, and it can generally repair that track. Because of the DNA, you have conjugate strands of the DNA. If it shoots one piece of the DNA off, each piece of the two strands of the DNA can copy from the other strand of the DNA, and so generally you can repair that damage. But if you knock out two of the strands, one behind the other, and the way in which you do that, you get what's called a double strand break. That's mostly done with some very, very heavy alpha particles of very high energy. And that's what you get from this, from uranium. Uranium produces heavy alpha particles with high energy, about 5 million electron volts. And so if this particle is inside you, inside Miranda somewhere, she doesn't get one track per cell per year. She gets as many tracks as you saw on the screen there in 30 days. Now that was a 30-day exposure, what we saw there. What we saw there here was a 30-day exposure to a special kind of plastic here. This is the plastic. It's called CR39, and what this does is it registers tracks. So you put it on top of the sample, in this case the sample from the Lebanon explosion that killed Hassan Nasrallah, and which a lot of people think was a uranium bomb of some sort, and we'll talk about that again some other time. So you put this on the soil sample. The soil sample shoots off these tracks, and there it is sitting on the top, and you get these bubbles that you see there. Each one of those is the end of a track. So in other words, you're looking along. So the bubble is this. That's the track, and the bubble that you see is the end of the track. We also have some air filters. But back to Miranda. Of course, Miranda now, with these particles inside her, she's inhaled the particles because they're everywhere, and she's a little girl now living in Gaza, or living in Beirut. And she inhales the particles, they get inside her, and they irradiate with a very, very high intensity just the volume around the particle. And that volume, because of the track length of alpha particles, which is about 40 microns, that consists of just the cells around this particle sitting inside her. And of course, when we look at the effects in Iraq and at the work I did in Fallujah, what we discover is that it produces an increase in genetic damage and cancer. So you've all seen the pictures there of the children with congenital malformations, horrible pictures. I won't show you any of them, they're too frightening. So the reason that this is important is because we have to change the way in which society, in which people understand the health effects of these particulate radiations. And they have to realize that that these things are not properly legislated against under current laws. I have told you about the particles and their effects, these particles. But let me finish by showing you how we did this and say a few final words. Science nowadays is about arm waving and experts. So experts do calculations and show you that something that most people can see perfectly clearly with their eyes cannot be happening. This is increasingly the case as time goes on. But science really is an empirical process. What you do is you do experiments and you look to see what's there. And this is what we've done. We look to see what's there in the case of these particles. So I thought you might like to see how we did it. Because really it's very simple. First of all, the samples were sent to us from Lebanon. They were collected at the impact site of the Israeli bombing that resulted in the death of Hassan Nasrallah. And these particles were sent to us disguised as coffee. It consisted of 3 soil samples, and this is an actual sample here. This is a sample of an ambulance air filter, and so that's contaminated with particles or whatever material was in the air when the ambulance engine was running. So we got these particles, we got these samples, and then first thing we did was we tested for radioactivity. Of course they might have been extremely radioactive, in which case it would have been dangerous. So we took the plastic packages that they came in out of the coffee, and we tested them with a normal Geiger counter. This is a normal Geiger counter. This measures gamma and beta radiation, this thing. It's clicking away here. This is the background in this room, quite low. I can expose it to a beta emitter, which is this thorium mantle from a Tilly lamp. And you see there's quite a big dose there, there's 10 microsieverts per hour there. But it's beta radiation, so it doesn't really harm you very much unless you eat it, which I'm not going to do. And this beta radiation can be stopped by copper, so it doesn't go very far into your body. So here's a piece of copper, quite a thin piece of copper, look, see? But on it, with the copper in the way, there's no signal, or very little signal. So most of the beta radiation is stopped by the copper, as you see. And alpha radiation is much shorter range, and that's stopped by a piece of paper. But I can't show you alpha radiation with this thing, because the window of the Geiger counter is enough to stop the alpha radiation getting through. To look at alpha radiation, you have to use a scintillation counter, where the window is very, very thin. And so, of course, then we did that as well. So we took the sample, and here's the sample, and we put it in lead to shield out the background radiation. This is the actual sample. This is the filter here. See this? This is that filter, cut into strips and placed in a Petri dish. And so we bring this down, and this machine here, which was bought for me long ago by the Irish government to look at the effects of Sellafield on the coast of Ireland. Quite an expensive piece of gear. They don't make them anymore, these people. So we put it inside this lead castle, and we measure the alpha and the beta radiation. The alpha, this thing discriminates between alpha and beta. So for the beta, a gamma, it goes click, 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 click. But for the alpha, which has got a slightly longer decay cycle, it goes beep. So what you hear is click, 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 beep, click, 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 beep, and so on. So you can see how many alpha decays come from the sample. But in fact, when we did that, we found that if we compared all the 3 samples, there was no real difference between them. So we had to, which meant that this thing was not sensitive enough given the amount of material we had. We only had 10 grams of each material, which is very little, about 2 teaspoonfuls. So we had to fall back on CR39. CR39 is a plastic. I've spoken about how it works. Basically, you put a piece of this, you can imagine as a piece of CR39 here, plastic. You put it on top of the soil sample, and you leave it for a long time. And every one of the decays there makes a hole in the surface. Well, it doesn't make a hole. It makes a a weakness in the surface of the plastic that you can then develop by putting it in concentrated potassium hydroxide. So we take the CR39. This is an actual CR. This is one of the CR39 slides. In fact, here it is. So that's what it looks like. I mean, I think I showed it to you already. And we put it on top of the sample inside a vacuum desiccator, which this is what this thing is, a vacuum desiccator. And there's the sample. That is an actual sample. That is one of the three samples. This reddish soil. You can see, I don't know if you can see reddish soil, but that's what it is. And then we put the plastic on top of that and shut this down. And that keeps out the radon. There's a lot of radon in the atmosphere. And the radon in the atmosphere clearly affects the signal. And so you have to put another piece of plastic in there which is not close to the soil, and that's your control. So then you see you can measure the number of decays on the plastic that's not the control and compare it to the number of decays that you get on the sample itself. And of course, if the sample is sitting on some hot particles, so there's lots of material here, but somewhere there is a hot particle, here it is, you get a lot of tracks in one place. See that? That's what we see, which I showed you before on the screen. So the reality is really a result, or not the reality, the result is what you get when you do this experiment. So we take this CR39, or this thing, once it's been sitting in there for 30 days, and we pop it into concentrated sodium hydroxide, in this case potassium hydroxide. Here it is. Very, very powerful, dangerous stuff. It will burn a hole in you very quickly. It's probably the worst thing that you can get splashed on you. It's much worse than sulfuric acid. Anyway, so you have to be a little bit careful. But anyway, I'm a chemist, you know, from long ago, so I am a little bit careful, although I must say I have blown myself up a few times. And so you put that into a beaker of this potassium hydroxide, and you heat it up to 80 degrees with this hot plate thing, which you can control with a rheostat, so you can make sure it is 80 degrees and it doesn't go up and down. You know, you can alter this is a voltage conversion thing called a rheostat, so it turns 240 volts into 230 volts or 220 volts or 180 volts or whatever. And so you can figure out what level of voltage you need to put into this to get the right temperature. You can get machines that do this automatically, but I don't have one. This is Chinese. Costs about 30 quid. So there we are. So then you boil it up. Then after you've boiled it up, had it in there for 5 hours or 4.5 hours at 80 degrees centigrade, you pick it out with some tweezers. Here we are. See, got everything here. There's the tweezers. You pick it out with the tweezers and you wash it off with water, and then you dry it, and then you stick it in a microscope. Well, you've seen what happens when I was at the other microscope is the little Vickers, which is an overhead illumination microscope. This is an inverted microscope. You can use this, or you can use an ordinary microscope, which one of those is phase contrast microscope. It's an old Olympus microscope from long ago. So you don't need stuff that's terribly expensive. I mean, you can't get this thing for nothing, but basically it's not terribly expensive. And the result is what I showed you. You see, extraordinarily, that these samples contain these hot particles. And not only do you see that, but we discovered that the particles produced an impact on the underneath of the plastic plate. And remember, this is sitting on top of the sample. There's the sample, okay? So the plate's sitting on top of the sample. And there's sample all around it too, like you see in the dish there. But somehow, hot particles appear on the top of the. So when I turn it upside down, you see, this is the bit that's facing the soil material. See, here's the soil material in there. And this is the bit that's facing the soil material. Imagine, well, I'll show you. There it is. So there's the soil. You can imagine it's in there, and there's the plastic piece of CR39 sitting on top of it. But of course, all the time that it's in there, the hot particles are coming up out of the soil sample, and because there's a lid on it, they haven't got anywhere to go. See, I mean, if this wasn't on there, of course they'd go into the desiccator and wander about and stick on the walls or whatever. But I can't look at the walls with a microscope, see, but I can look at this thing with a microscope. And I had this on top. This was unexpected, incidentally, and very interesting and important. So what we found is that these hot particles turned up on the opposite surface of the plastic, which meant that they came up and they went down like this. And of course, because when they're inside the matrix, when they're in the soil, they have to break out through the soil. So some of the tracks that you get are a little bit sort of wongly, because they must hit a soil particle and bounce off it, you see. So they're not all in the same place, but all of the tracks on the top were all absolutely clustered together, which means that the particle was a pure uranium particle, or maybe uranium-235. We don't know. It may have had plutonium in it or whatever. But anyway, it was probably a pure uranium particle, which a U-238, U-235, U-234 particle sitting that had come out of the soil and dropped down on the surface, on the opposite surface. And the image that we got was fantastically good. So that's how we did it. That's how we did it. So let's pull this all together. What is it that we've done, and what is it that we know, and what is it that we've discovered? Well, what we've done is we have looked at 3 samples from the site where Hassan Nasrallah was killed following a bomb by the Israelis on the bunker where he was. And the samples that we obtained from there have shown the presence of uranium particles. So that's the first thing that we've done, and I think that's quite important. We've succeeded in showing that the Israeli bomb was a uranium bomb, and in fact the first person on the scene obtained some samples which he handed to another colleague, and that colleague, one of the people who sent the samples here, incidentally, or was associated with that, one of the 3 heroes that got the samples, he sent the sample to a French lab that said that it had a lot of uranium in it. So we already had a good idea there was a lot of uranium in it. And what we found is that the uranium is in the form of these hot particles, and that's a first. That's the first time that these have been imaged from a site like that. But the other very important thing that we discovered as a result of the work that we did, as I showed you in the lab there, is that the particles become airborne on their own. So some effect that they have, some electrostatic effect, causes them to become airborne, and that's very important, because that means that where this material is in the soil, those particles are becoming airborne, and people who are living in those areas, this area is Dahiye and Beirut, are inhaling these particles. And you may be sure that all sorts of other areas where the Israelis have been bombing with similar weapons, in Gaza for example, where we can't get samples, those people will also be inhaling these uranium particles. And we know, following the Iraqi wars of 2003 and 1991, these particles are very harmful, that they cause increases in cancer and genetic malformation and all the things I talked about when I was introducing this issue. So this is science, this is reality, these are experiments, this is what science is. It's empirical evidence. You go out there, you look out of the window, you see something, you do an experiment, you look at it, you detect things, and you report it. And so I'm very happy to have been able to make these discoveries as a consequence of these samples which I've got. More samples are coming from all over the place, and we'll need a certain amount of money to get them analysed in laboratories where we can look at other aspects of these samples. For instance, gamma radiation from neutron activation products and the ratio of the uranium isotopes, so we know what kind of bomb is being used and all of these things. But so far, I think we've made a great leap forward. Don't you? Thank you for listening.